We're going to head into, as promised, Friday, that we're going to start looking at heteronuclear diatomics, so diatomics with two different elements, and specifically these are going to be ones that serve as ligands to metals, and so as we learn more about their MO diagrams, we're going to understand better the bonding between those molecules and metals. But there's one thing that I wanted to mention before we get into the MO diagram. We're going to use CO, carbon monoxide, as a case study. So, but there is this anomaly that shows up. And this shows up with these diatomics that have boron, nitrogen, or boron, carbon, and nitrogen in them. And it looks like this. So we have, with all these second period elements, we are always seeing the same kind of pattern where we've got the 2s atomic orbitals and the 2p atomic orbitals. And as usual, we expect to see the sigma and sigma star originating from the 2s. But this is the thing, with these small elements, starting with boron, and honestly, we don't mention lithium and beryllium because this would hold for them as well. But lithium and beryllium, they act as metals. They're not undergoing a lot of covalent bonding, so that's why we just don't mention them. So we're looking at the nonmetals here, and that they're small elements, and their 2s and their 2p orbitals in terms of energy, they're really close together. And so what happens is there is an energy mixing that goes on. And the result of that energy mixing is that there is actually a skewing in the overall pattern of the energy order of these molecular orbitals that result. And so what we observe is that instead of the sigma molecular orbital being lower in energy that we see once you start with oxygen and you go on for the rest of all the other nonmetals, it's the way that we saw on Friday. It's that same order. But with boron, carbon, and nitrogen, this is any molecule that has those. So it could be, we're going to see it in CO. It could be combined with one that doesn't see that. But if one of these appears in the molecule, we're going to see this. And so the bonding pi molecular orbitals are lower in energy. Then we see the sigma. Up here, it's the same. So these are unaltered because they're not mixing with anything. They're just energetically, they're way up yonder. They're not affected. It's just these with all this mixing. The 2p atomic orbitals are mixing down with the 2s and the 2s, and all this funky stuff happens, so we end up seeing these pi being lower in energy. How do we know this? Okay, or what was the first indicator? Let's look at this. So in the context of this molecular orbital diagram here, this would be relevant for boron. So let's B2. So let me put a line here. Okay. So if we look at this as the MO diagram for B2, let's put in the electrons. Okay, so how many electrons do we have? How many valence electrons does one of these borons have? 3, yeah. So it's got 2s2, 2p1, each one of those has that, so we can put those in. Okay. So then when we take all 6 of these electrons, we put them in, we use the Aufbau principle. Here's our 4, and here's our 2. Okay. What can we say about the magnetism of B2? Do you remember our 2 terms that you learned? Paramagnetic. B2 is paramagnetic. What would B2 have been if this skewing didn't happen? It would have been diamagnetic. So with the normal pattern, that we see for like O2, B2 would be diamagnetic. If all electrons paired up. But when B2 was studied and it was determined to be paramagnetic, it was like, wait, what? And so with more spectroscopic experiments, where are these electrons going, hitting them with photons, and they're moving around, and then analyzing the data, it was overwhelmingly supporting that there is this skewing going on. So we see that again, and that's been supported now for any of those diatomics with those three. Okay, so keep that in mind when you're creating any MO diagrams. It has these three that you will see this kind of skewing, and generally speaking, these anti-bonding molecular orbitals, these will always be higher in energy, but just weird things happen here. But we do see this order. So the order is either going to be like that or like that, depending on what's in there. So let's now take a moment and then think about the energy, relative energy, and handed out those atomic orbital energies. So you have those. We're going to know what those are. But then also relative to one another visually. I wanted to show a diagram that can show this. So, okay, I think my laptop is charged enough. Okay. Come on. All right. Slideshow. Oh gosh, wow. Come on. It's hi. Okay. Okay, cool. I'm gonna turn it down. Okay. So we can pretend like, I'm sure in a lab people have made diatomics with lithium beryllium. That's fine. And here we are with B2, and we see these. So SOMO, HOMO, LUMO, you talk about those a lot in organic chemistry, and then maybe SOMO, the singly occupied. I don't know if you use that term. That's what SOMO means, singly occupied, that we see with paramagnetic species. Okay. And overall, we are seeing, I want to show, I feel like, yeah, here we see that, this is what I want to show better, is the relative energies, all right, that we're seeing, that going across a period, we have that trend of effective nuclear charge. So as you go across a period, what is the trend with effective nuclear charge? Increases as you go across, yeah. Increases as you go across. So greater pull from the nucleus, those orbital energies are going to go down. Lower in energy, more stable. We saw that with atoms. We see that with molecules. So same kind of thing going across. So whenever we're comparing, like we're going to be looking at carbon, oxygen, carbon monoxide. So along with actually having the values, you have the values on that valence orbital energy table that I handed out. You have the energies there, but you also know intuitively, you don't even need those values. You will know that the oxygen orbital levels will be lower than the carbon. So when you're combining them together, these are looking overall C2, N2, O2, all of those, but that's going to help you when you're creating these molecular orbital diagrams. Okay, and then this one that I had started with. Okay, this is now filling these MO diagrams, and it shows like we just looked at with B2. Here is where we see this is paramagnetic. And then our C2 would have been paramagnetic if everything was normal, but now it's diatomic, okay? N2 was a little bit tricky for a while. It was unknown with N2 which order it was because they're all full. So it's like, well, either way it's going to be diamagnetic. So they had to do a lot of spectroscopy to assert the claim. And so I think everyone, for the most part, agrees that the order for nitrogen is inverted, but you will see in some textbooks it doesn't show it inverted. So don't be surprised if you ever see that in a textbook, because either they're simplifying it for Gen Chem students, don't want to confuse them, or that was printed before that controversy was alleviated. So sometimes you see things incorrect in textbooks. It just happens. So, all right. So let us create. We can turn this off for now. We're going to create this MO diagram for CO. And some of this you will be able to do no problem. And some of it is a little less intuitive. So we'll do it step by step. And we're going to not only look at the energies like we did last time, but we're also going to look at the molecular orbitals and their shapes, because they do differ from what we see with those perfectly symmetrical homonuclear diatomics. So we're changing things, we're changing energy levels, and changing shapes. Okay. So convention is, let's see. Convention is to essentially, if you look at the periodic table and you see CO, then we usually put CO, and that's usually what the formula is anyway. So that's how we usually follow it. And then we're going to end up with CO in the middle. Okay. So starting out here and using your, oh, Parker, there's a handout right there by the door, yeah. And then using that handout, start putting in, drawing the MO diagram, starting with the valence, atomic orbitals, and writing in those energies of the atomic orbitals relative to one another for the valence shell. And you can start thinking about what, mixing the 2s together and thinking about what those are going to look like, what those molecular orbitals will look like.